All right. Day two, confidence intervals for means. Yesterday, we talked about some stuff concerning confidence intervals for means, like the t distribution and things like that. So there's a lot of new things. Make sure you watch that video as much as needed until that stuff about the t distribution kind of sinks in. Also, make sure you read what the book says about the t distribution to get a little bit more background knowledge on it as well. All right, so today what we're going to do is we're going to take another look at constructing a confidence interval for a different set of data. Yesterday we did M&Ms. Today we are going to take a look at estimating the mean mass of a snowflake. Yes, I know that is weird, but I found this data set in an old folder, which means at some point somebody taught this class and actually measured the mass of 40 snowflakes. I don't know how they did it, but it was too interesting of a data set to pass up on. So we're going to use it today, and we're going to estimate what the mass of a snowflake is with 95% confidence. The sample that I found had 40 snowflakes in it, and I recorded the actual data here. And what I want you to do before we start, I want you to go ahead and pause the video, and I want you to actually put this data into L1 on your calculator. So I actually want you to, go here and turn this on in case you forgot how to do that. So I want you to go to Stat, Edit, and then right here in L1, I want you to actually put that data into L1 for today's exercise. Okay, so let's go back to our notes here. Okay, so hopefully you've got that entered into your calculator. When you do your 1var stats, these are the numbers that you should get out of your 1var stats, and make sure that those are exactly the same. That'll let you know that you have the data entered incorrectly to your calculator. All right, and we're gonna go ahead and just kind of run through the motions with the stuff that we learned yesterday. We're gonna start building this confidence interval from scratch. First, we need to make sure that we can actually make a confidence interval for this thing, that we've established the requirements for a normal distribution. Okay, and we do because our sample size is large enough. We had a sample size of n equals 40. So in this particular case, n is greater than 30, right? 30 is that magical number where the sampling distribution is close enough to normal, where we're confident enough to use a normal distribution or one of the t distributions. Okay, so n is greater than 30, so the sampling distribution is also normal. Okay. And then it says quantify how variable the sample mean is for our sample of size 40. In other words, they want us to calculate the standard error here. So remember, our formula for calculating the standard error means that we have to take the population standard deviation and divide by the square root of the sample size. And we ran into this problem yesterday. This is the big key to everything with the t distribution. We don't know what this is. To know what this is, we would have to measure every snowflake in existence and find the standard deviation for every snowflake in existence. We're never going to know that. We're never going to know this piece of information. All right, so instead, right, we make a substitution. We use our sample standard deviation instead of the population one, and this is what forces us into the t distribution family that we learned about yesterday. Okay, so our sample standard deviation was 0.1, and our sample size was 40, so I'm going to put in a square root of 40 here in the bottom, and if I go to my calculator and input that correctly, I should get a 0.0158, and this will be our standard error. Okay, that's another key piece of information. Also, don't forget that our sample mean that we collected here, this is our point estimate. Another key piece of information that we need. All right, so now that we've made that substitution, right, and we've made the substitution for the standard deviation here, population to sample, that means we're going to be using this t distribution family because we need a distribution that models the variability of the sample mean and the sample standard deviation, since we made that substitution. Okay, and we need to make sure that we understand the degrees of freedom in the sense of, like, we need to know how to calculate it Like I said, if you want to read more about what degrees of freedom are and what they mean in mathematical theory, that's fine. But you don't necessarily need to know that for this course. Okay, so for our problem, our sample size was 40. So to calculate the degrees of freedom, I just take 40 minus 1, and we're going to get 39, right? So we have 39 degrees of freedom. And we need that to calculate our critical values, right? So remember what we want, since we're doing a 95% confidence interval, let's say this is the t-distribution that we're going to use. We want to capture 95% of the distribution in the middle. So we got our 0.95 in the middle, which means what's left over for the tails is 5% split in two. Right? So each tail is going to have 0.025 and 0.025 on the left and on the right. Okay? And these values down here, those are the critical values that we're trying to find. So to find those, we need to run an inverse t, not an inverse norm, but an inverse t, since we're using the t-distribution. We're going to tell it the area in one of the tails there, which is a 0.025, and then the degrees of freedom, which is 39. Okay? And if you put that in the calculator correctly, you should get a 2.02269. I don't know why I carried so many decimal places there. You could probably go to 3, maybe 4 decimal places, and you should be fine for most of the MyOpenMath problems. But do be careful with the intermediate rounding. All right, so if you're getting something wrong, check that intermediate rounding, try the problem again, and see if that's the issue. Okay. All right, so we got our critical values. So we're at that point where we are ready to construct and interpret our confidence interval. Before I do, I just want to make sure that I have all of our key pieces of information here. We know the point estimate. We got that from one var stats with our data. So we should have gotten 2.95 here. Our standard error, we calculated that to be 0.0158. Our critical value, we just did that with the inverse t. We've got 2.02269. Our level of confidence is 95%. And then to calculate our margin of error, we just multiply these two guys right here, standard error times critical value. And we will get, I got 319. And so that's my margin of error. Again, our recipe for a confidence interval is to take our point estimate right, plus or minus the standard error times our critical value. We'll call it T alpha over 2. Right? So our point estimate is 2.95 plus or minus our standard error, which is 0.0158, times our critical value of 2.02269. And we essentially have our confidence interval here. We just need to multiply our two values here, which gives us 2.95 plus or minus 0.0319, which is our margin of error. So there's our confidence interval. So we can say with 95% confidence that the mean mass of all snowflakes is between 2.95 plus 0.0319 or 2.95 minus 0.0319. And that's what I'm going to work on now, is just creating this interpretation statement. Right? So we want to start it off with, I am 95% confident. That the mean mass, right? Give it some context. Talk about what it is you're estimating, right? So we're going to say the mean mass of all snowflakes. Right? I'm 95% confident that the mean mass of all snowflakes is between. And then we're going to do 2.95 minus the 0.0319. If we put that in the calculator, we should get 2.92. And then if I do 2.95 plus 0.0319, we should get 2.98. And this was measured in milligrams. So you should include your unit on there. I'm not a big stickler for this kind of stuff because I'm a mathematician, so honestly I don't really care too much about units and things like that, but scientists do, and they're the primary ones who use this stuff. So make sure you put a units there on the end. I would make sure that you kind of go through these, make sure you know how to calculate each of those critical pieces of information. And what I want to do here is I want to get my calculator out, and I want to see if I get the same thing from my calculator using that t-interval feature I showed you in the last video. Okay, so let's put this over here. And remember how I had you put the data into L1. This is where we're going to use that. So I'm going to go to Stat. I'm going to go over to Tests, and I'm going to go down to t-interval. And remember yesterday we went over to stats and just entered in the stats that we found from the 1var stats. We don't actually have to do that. When we have the raw data available to us, we can actually just put that into L1 and tell the calculator where the data is. So you just tell it, hey, use the data that's in L1. Don't do anything with the frequency, just leave it as a 1, and then tell it what confidence level you want and hit calculate. And there we go. We get our confidence interval. We got 2.9181 rounded. That would give us the 2.92 that we got over here. Pull that back up. And then our 2.98, we can see that. So we're good. And we got the same mean and the same standard deviation that we got from the problem before. So this is looking good. We got that problem right. Okay. So that's how you use that other part of the t-interval feature, again, using the data part versus using the statistics part that I showed you yesterday. All right, what I want you to do at this point, right? So that's another run through of another problem there, kind of explain this thing in great detail. What I want you to do is I want you to turn your notes over. You should have the second page where they are, they're going to estimate the mean mass of an adult human brain. Okay, and real quick, I know it says 80% on your notes. I want you to change that to a 95% level of confidence here instead of an 80%. So make sure you make that change. And then I want you to pause the video, and I want you to try and run through all that same stuff just like I did on the first page. I want you to try and do it on your own. Okay, calculate the stuff, establish normalcy, do all the stuff, the same stuff that I did on the front page on your own, and then click play again. And I'm not going to explain every single step here, but instead the answers will kind of pop up on the screen here for you so you can check yourself. All right, so go ahead and pause that video and give it a try on your own. All right, guys, are you ready? Get it all done, ready to check your answers? Here we go. I'm going to put them up on the screen. There they are. One of the things I will talk about before I end the video here, this first part where we establish the normal distribution can be applied. Notice that the sample size is not 30, it was 14. Okay, but because it's stated in the problem that the population of adult human brains were normally distributed, so they kind of told us that the population was normally distributed, we don't need the sample size to be above 30. So if it starts off normally distributed, it's going to stay normally distributed as we do those repeated samples. Okay, so that's how we were able to get normalcy here. But if we didn't know that about the population, if they didn't tell us this and this was below 30, we wouldn't be able to do the problem. We would say NA or the sample size isn't large enough to continue here. All right, so be wary of those types of problems on MyOpenMath. Make sure you're establishing that normalcy before you continue on into the problem. All right, guys, good luck. Make sure you tune in for video number 3.